Now we're ready to talk about energy production. This is a unit where a lot of things come together, a lot of the previous ideas come together, and so this will be a good opportunity to wrap things up for our first year of IB physics, and yeah, it'll be good here. So when we talk about energy sources, primary energy is energy found in nature that has not yet been subject to processing. Secondary is where sources have been processed or exploited, and secondary energy is produced. So it must be suitable for use in machines that can do mechanical work. So when we talk about, secondary examples, we're burning fossil fuels, that kind of thing. Primary energy would be like a hydroelectric dam. You have water that's up above and can fall down, and you have, energy, just intrinsic in what it is. Here's some other examples, particles of air moving, windmill, taking air to turn a generator. And then, secondary, again, exploding fuel and air mixture to move a piston, right? So burning fossil fuels inside a engine. Specific energy is a huge idea. This is the amount of energy that can be extracted from a mass of fuel. So how many joules per kilogram you can get. So in other words, if you had 1 kilogram of coal and you burned it, you would get 30 megajoules. With wood here, if you burned wood, you would get 16 megajoules for every kilogram that you would have. Gasoline, 47 megajoules per kilogram. And so this is a really helpful way to compare different kinds of fuels that we would have. So let's take a look at an example here of how we can go about this. A truck is 35% efficient and requires 60 kilowatts of output energy. The energy density of gasoline is 47 megajoules per kilogram. We want to figure out how much gas in kilograms will be needed for 30 minutes of travel. So the first step of what we'll do here is we consider this, the engine is only 35% efficient. And so what we can do is we can look at the efficiency equation like we did before. Now, something else that's really helpful here, if we look at efficiency, what you get out over what you put in is, in general, how you look at efficiency, right? So in other words, how much work do you get for the heat source coming in? And so we know power, right? Power is energy over time. So if we look at 60,000 watts, which is 60 kilowatts, 60,000 watts per second is what that means, right? So that's what we need. That's the work that we need. So in other words, what do we need for QH here? Well, we would need a lot more heat source, right, than just 60,000 joules each second, right? We would need a lot more because we're only 35% efficient. So, in other words, if we look at this with, energy per second over here with power is energy over time. This is essentially, 60,000 kilowatts is for every single second, 60,000 joules. And so that's the work that we need, but we're going to need a lot more in our, heat source here. So in 30 minutes, we have, 1,800 seconds. We know the power, and so we need to know how much energy that is, and so that's that many joules. So that's how many joules we need. Now we know that this is the energy density right here, 47 megajoules per kilogram. So if we divide that, we'll be able to figure out how many, and then 1 over kilogram times, the kilograms are gone, and we end up getting, 6.6 kilograms is how many kilograms of fuel we would need. Now, if we were 100% efficient, we would need much less kilograms of fuel, right? But we have to get that total amount. Now, energy density is the amount of energy coming from a certain volume of fuel. That's how many joules per meters cubed that you have. And so we're going to need to be able to go back and forth from each of these. So if we have energy density, that's how many, Q per volume of fuel. that we have. So, how many joules per, meters cubed that you have. Now, you could have different units, right? You could have that, uh, you know, within, centimeters cubed or whatever. But so just make sure that your units cancel out. We know density equals mass over volume. So we can rearrange this, and instead of volume, we could put mass over density, place that in there. And once we have that, we can rearrange the equation, multiply the top and bottom by density, and that's gone there. And so Q over M, right, that's specific energy right here. And so that's how we get specific energy, or how we get energy density from specific energy, or vice versa, right? We multiply the specific energy by density. So you will need to be able to drive this, and it'll be a good idea to practice this, because you'll need to be able to, go back and forth easily with that. So let's take a look at an example here where we have the density of uranium is 2 times 10 to the 4th kilogram meters cubed. The specific energy, actually, no, that should say energy density there. So that's my mistake. So energy density is this 1.3 times 10 to the 18th joules per meters cubed, and we want to find out how much energy is in 3 kilograms, right? So what I want you to do is pause the clip, practice the derivation that you just wrote down from scratch, so without looking at it if you can, and then go ahead and solve the problem. And so go ahead and pause the clip, give that a try, and when you're ready to check, you can hit play to continue. Okay, so we've got the 1 kilogram of uranium-235, and we rearrange our equation there, make sure your derivation's okay, and we end up getting, the specific energy times density equals energy density. So with this, we know the energy density now. We know the density itself. We're looking for the energy. We know how many kilograms we have. So we have the specific energy, which is, or the energy density rather, and I have to fix those slides. And then we divide both sides by the density itself, and so how many joules we get per kilogram is this. We have 3 kilograms, so the total amount of energy we would get would be 1.95 times 10 to the 14th joules. All right, so in this one, we're considering a hydroelectric dam, and we want to find out the specific energy of the water used in the hydroelectric power plant if all the water that falls is converted into rotational energy, and the fall is from 80 meters. And so why don't you pause the clip and give this a try, see if you can reason through this. And this is more conceptual than anything almost, and at least initially. So go ahead and pause the clip, give this a try, and then when you're ready to check, you can hit play to continue. All right, so basically, we know that specific energy is how many joules for every single kilogram do you have, right? So if you have a kilogram of water that's at 80 meters, what kind of energy does it have? What has gravitational potential, right? So that can be turned into mechanical energy, which is what we see here. So, all of that potential turns into mechanical energy. So therefore, 1 kilogram of water will have this many joules. So that's actually the specific energy, 784 joules for every single kilogram in this power plant. Well, the hydroelectric power plant. So what I want you to do now is go ahead and convert this to how many megajoules per kilogram that we have for this particular situation. So go ahead and pause the clip and do that. And when you're ready to check, you can hit play to continue. All right, so we should get 7.84 times 10 to the negative 4th megajoules per kilogram for this particular situation. If we had a different kind of dam, right, that could be a different situation. Now, it's important to know the advantages and disadvantages of each of the different types of situations, energy situations. For hydroelectric power, the advantages is that it's free, right? You're getting your resources there from a flowing river. It's inexhaustible, it just continues flowing, and it's clean. Now, the disadvantages is that it's very, very much dependent on the location. Changes the environment dramatically, or well, it changes the environment dramatically, right? So you set up a dam, it's going to flood a whole area, so that can be a big issue. And then the initial cost is high. All right, so let's talk about some non-renewable sources. Oil is non-renewable, right? So once you use up whatever oil that you have, if you burn it or whatever, you can't replace it very easily, right? It takes a long process to get oil. Natural gas, same situation, as well as coal. All of these take a long, long, long time to form, right? So once you use it up, you can't use any more. Nuclear fuel as well, right? So you use up the uranium, it can't be renewed. So non-renewables are finite. They're being depleted much faster than they can be produced, and that's an issue, right? So let's talk about some renewables. Solar, right? So you're not going to run out of that. You can use it. Wind as well. The wind's going to pass through, and you're always going to have the wind there. Waves, waves can be used. Hydroelectric, right? So you have the water flowing through. And we got that. Now, fossil fuel, when we consider fossil fuel, it includes, oil, coal, natural gas, and they're produced by the decomposition of buried animal and plant matter, where you have high pressure and, you have bacteria there. So fossil fuels take a long, long, long time to be produced. And burning these, is the traditional way of using them. Now, in coal and oil electricity, into electricity, right? So you burn the coal and oil. And then what happens is, as you burn it, you can heat up water, and that water can turn into steam. That steam can then go into a turbine, spit a turbine, and then that can go and turn a generator, and then the generator produces electricity. We're going to get deeper into this once we get into electricity magnetism next year. So advantages of fossil fuel, they're relatively cheap while they last. You just collect them, and use them, refine them if you need it. High power output, right? So the energy density is pretty decent there. Many engines and devices can use them easily, right? You can, put fuel in a car. It can be sent into the engine, right? Pretty straightforward there. And, we already have a huge distribution network, right, of being able to drill and get it and then distribute it. Disadvantages, eventually run out, and, we're polluting the air with the gases, including the greenhouse gases, which we'll talk about. Now, just like we looked in thermodynamics, we know that energy is conserved, right? And so, however, energy can be lost to the outside, right? So you're never going to have a 100% efficient system. And, we learned that about the second law of thermodynamics. And so we'll be able to harness a lot of it, but, there's still going to be a lot that we can't harness. One of the key parts that I wanted to highlight at this point too are the Sankey diagrams. Sankey diagrams are always drawn to scale. So if you notice here, here's the combustion. This is the energy coming from combustion, right? Now, if you look at the sliver, the green sliver here, this is the effective power. We're only getting 25% as diagrammed here for this particular engine. So you can see the other ones here, right? Friction loss, coolant, what's going out the exhaust, and all of these sections are proportional, and Sankey diagrams have to be drawn, proportionally there. All right, so let's take a look at this situation with a power plant that is producing electricity by burning coal. The thermal energy produced is used to make steam, right, and then turn a turbine. And let's say that the power plant is an output of 40 or 400 megawatts and operates at 35% efficiency. So let's calculate the rate at which thermal energy is provided by burning the coal, and then calculate the rate at which the burning, assuming this specific energy is 30 megajoules per kilogram. So if we think about, the system here, right? QH is coming in, we have our output going out, and then we have QL, and we have a 35% efficiency, right? So we want to calculate the thermal energy provided. What essentially is QH? And that'll be good here. So if we think about, power is how much energy over a period of time. This is the output that we need, 400 megawatts. And so if we look at 1 second, right? So in 1 second, it would be 400 times 10 to the 6 joules every single second that's produced. And so with that, and with knowing the efficiency, we can work our way backwards to find QH, as well as the rate at which coal is burned, how many kilograms we would need to burn, in a period of time. And so, yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so efficiency is how much work we have in a period of time. Our QH that needs to come in here is 1.143 times 10 to the 9 joules. And we need that every second, right? So therefore, if we have this many, megajoules per kilogram, we're going to need this many joules, okay, so this is how many joules we get for each kilogram, right? So, how much energy we need per kilogram, right? So the rate at which coal is burned